Okay, welcome back, Organic Chemistry 2341. We're going to continue on with Module 8, which is we've already done in the alkene section, and now we're going to do the alkyne section, okay? So I do have a guest speaker who's supposed to show up sometime today. I don't see them in the participants just yet. So what I will do is I will go ahead and start with my slides modules 8.2 until they log in and make themselves known. They're going to talk to us about a special scholarship opportunity when they log in. And I don't see them. So I'm going to go ahead and start. Let me go ahead and share my screen. And let's see. There it is. I see it. Does everybody else see it? All right, excellent. Okay, so we're going to continue on with our module with double bonds, okay, and triple bonds. So we have pi bonds, and the reactivity of the pi bond is actually fairly unique. It's not like the substitution reactions we're doing. We're doing additions across these double bonds, and we have several different reagents and mechanisms that we were playing with to go ahead and see that. So what we're going to do now is we're going to see what effect having a second double bond on that system does to our reactions. Okay, some of them are exactly the same and some of them are a little different. So we need to pay attention to which are the same and which are different. Okay, so we all know what alkynes are. It's a triple bond, it's two pi bonds, and they're opposite each other. We also know that we have this triple bond. It's a very short bond, it's a very strong bond. And we saw that with IR because it's one of the higher frequencies that vibrates. And we also saw something special about the carbon-hydrogen bond there. Because of the hybridization, we saw that proton on the alkyne was the most acidic of the hydrocarbons. It had the most S character. It had the lowest pKa. It's the most acidic. So that's telling us something about the alkyne itself. The other cool thing about the alkyne is because it's the most acidic, if we have a terminal alkyne, we can take that proton off and it becomes an anion. And remember, anions are nucleophiles. So we have an excellent nucleophile in the acetylide ion. Okay, so what does that mean? Well, first of all, the pKa is around 25. So we can't just use something like hydroxide or alkoxide to remove that. We have to use a much stronger base. And we have two strong bases we tend to use with this material. One of them is called sodium amide, and we use that in ammonia as our solvent. But then the other thing we can use is what we call butyl lithium. Notice it's the 4 carbons with a lithium on it. We have a very polar carbon lithium bond. It's a polar, but it's covalent. But the carbon is now more electronegative. That means the carbon carries the negative charge. So it acts as a strong base and turns into the hydrocarbon and leaves the lithium on the alkyne. So we have two bases available to us to deprotonate our alkyne. Our sodium amide right here, and our butyl lithium right here. I see somebody pop in. All right, so when somebody pops in, we'll let them speak for a little bit. Okay, so now that we have a nucleophile, we have this nice negative charge on carbon, we can do just SN2 reactions. So if we had alkyl halides, it would do a nice SN2 reaction to make a new carbon-carbon bond. Notice the triple bond is in the product. All we're doing is using that carbon as our nucleophile. And so we have a triple bond in our product and we displaced some halide from our alkyl halide. So that's what happens when you do an SN2 reaction, okay? But the other cool thing acetylene can do is they can add across a carbonyl, okay? So we have a partially positive side of our carbonyl. We'll have our nucleophile come in and interact with it. And just like other reactions with carbonyls with a strong nucleophile is we get that tetrahedral formation. And because it's attacking a carbonyl, we end up with an alcohol at the end. Okay. So by choosing which carbonyl compound we attack, we can end up with a primary alcohol, a secondary alcohol, or a tertiary alcohol. So it's very important on which carbonyl you're attacking to see what you end up with at the end. So how do we get the primary alcohol? Well, you have to attack a carbonyl that has 2 hydrogens on it. And the carbonyl we have with 2 hydrogens on it is formaldehyde. So we have our formation of our acetylide ion. It acts as our nucleophile, kicks it out to our tetrahedral intermediate, and then upon acidification, it turns it into a primary alcohol. Okay. If you take any other aldehyde besides formaldehyde, you're going to get a secondary alcohol, because one of these hydrogens is going to be switched out for an R group, and you get a secondary alcohol every time. Now, to get to the tertiary alcohol, all you have to do is start with a ketone. All ketones give tertiary alcohols when attacked by acetylene ion. Okay, so primary is formaldehyde, any other aldehyde is a secondary, and all ketones give tertiary alcohols after being attacked by the good nucleophile, the acetylide ion. Okay, does that make sense? It looks like, that's the hydrogens were already on the carbonyl, so that's going to give us a primary, or the aldehyde. And then if there's 2 R groups, it's going to give us the ketone. I'm sorry, the ketone gives us the tertiary. Okay, so that's how we can use the acetylide ion itself as a nucleophile. But let's talk about trying to actually react that triple bond. We want to attack just the alkynyl bond, and we can do this with a variety of different ways. Now, actually, I want to talk about how to make the acetylene first. Okay, we have a couple different ways to do it, but for the most part, we have to use a very strong base, and we must have 2 equivalents of halogens and 2 hydrogens on adjacent carbons to make the double bond. We have 2 different ways to do that. The first way we do that is we have 2 halogens that are 1 carbon apart. Okay, we call those vicinal dihalides because they're in the same vicinity as each other. One's on the 1 carbon, one's on the 2 carbon. And when we have a hydrogen on each, we eliminate 1 equivalent of acid to form a double bond. We eliminate a second equivalent of acid to create our triple bond. Okay. Now, the first one we can easily remove with a base like hydroxide or alkoxide. However, the second one is much harder to remove. We're changing the hybridization again, and therefore we have to use very strong bases like sodium amide, the butyl lithium, and some lithium reagents we'll learn about too. Okay, so we have to have very strong bases to do this. Now, what if you had 2 halogens on the same carbon? If they're on the same carbon, we call those geminal. Geminal means twin, and so you have 2 halogens on the same one. As long as there are 2 hydrogens adjacent to that, we can eliminate 1, eliminate 2, and generate our triple bond. Okay, so the requirement is very strong base and at least 2 halogens with 2 hydrogens to be able to remove 2 equivalents of acid. Okay, so that's how we make alkynes. And so it's a little more, we made alkenes a couple different ways, and we made it by removing acid. This, we just need that stronger base to remove that second equivalent. Questions on that? Okay, all right. So the mechanism is basically the same as we saw in the alkenes, but it's got a second step to it. In the first step here, we like to have our E2 elimination happen where our base is pulling off the hydrogen and it's in that anti-configuration to the halogen that's leaving. When we do that, we end up generating the Z isomer in this particular configuration because this halogen, this R is back and this R is forward. Once we have that coplanar, we now have that similar orientation. The hydrogen and the bromine are in the same plane as each other. Our second equivalent of base comes off and removes our second bromine, giving us this. Now, whenever we have that, hydrogen is anti, or like on the end of a chair to the halogen or the whatever's leaving, it's always a faster reaction in E2. However, we can have a different conformation happen. If we rotated and used a different hydrogen for the system, okay, interesting, okay. Letting somebody in from there, okay. So if we had a slightly different configuration where our we removed a different hydrogen, we would end up with the E isomer right here. See the R groups on the same side. And this is a little bit harder to remove. It's slower, but it will still go. It will still give the same product here, but it is a much slower reaction. The Z isomer gives a much faster elimination to form our alkyne because of this anti-configuration. The leaving group and the hydrogen can be pulled off at the same time. Questions on that mechanism? So it's similar, so we just have to do it a second time on the alkene. Now notice that this intermediate here is why other bases won't work, okay? We can use hydroxide to pull this Sp3 hydrogen off. We can't use the hydroxide to pull the Sp2 hydrogen off. It's not as acidic. So we have to use that much stronger base, that sodium amide, the butyl lithium, or the other lithium reagent, the other amine reagent. So the fact that this hydrogen is our Sp2 hydrogen means that it requires that stronger base. All right, does that make sense? We can pull this one off with hydroxide, but we have to pull this one off with a stronger base, sodium amide or butyl lithium. Okay, so now let's get on to reaction. So in alkenes, we had addition of acid across it, addition of water across it, addition of halides across it, and then we had ozone and a bunch of the other things. So let's go through each of those and see how they're the same or different, okay? So in the case of adding an acid across the double bond, you can actually add one equivalent of acid, and it's going to add across that the triple bond, giving you an alkene with a halide on it, okay? The great thing is it's the same mechanism we used when we were adding hydrogen across an alkene, in the fact that it gave us Markovnikov's addition. The hydrogen was on the more hydrogenated side, okay? We have that exact same mechanism here. So when we add our acid across our triple bond, we're going to end up with our bromine on our more substituted carbon of our alkene, if possible. So we had the hydrogen from the alkyne here. We add the hydrogen from the acid there. So it adds Markovnikov, okay? Now, if you only have one equivalent, it will stop there. And it has everything to do with the idea that we're forming this alkenyl cation, which is more stable than the more substituted cation is more stable than the less substituted cation. And so we end up with addition of the halogen there. So with just one equivalent acid, it'll stop there. What if we add another equivalent acid? What's going to happen? It's going to add across it too, but is it going to add Markovnikovs or not? The answer is it's going to add Markovnikovs. It's only a slightly different mechanism in the fact that we still form that cation, okay? But this cation now has a resonance stabilized contributor in the bromine that's attached to it, okay? So if we add their first equivalent, we get our alkyl halide, our alkene halide. If we add the second equivalent, we end up with the geminal dihalide. Both halogens are on that same carbon, okay? This is a really clever way to get a geminal or two bromines on the same carbon. And the mechanism, as we predicted, was the first equivalent of HBr. It's going to generate a cation, which is going to put our bromine on it. Then the second one is going to want to generate the cation on the more substituted carbon, okay? We have one carbon over here and two hydrogens. We have one carbon and the bromine. The bromine can help stabilize that positive charge even more than a carbon can because it has lone pairs, so it can resonance stabilize the positive charge by having it reside part of its time on the bromine and the rest of its time on the carbon, making the carbon the most reactive site. So whenever we're adding a second equivalent of acid across a double bond, we always end up with the geminal dihalide, or them both on the same carbon. Okay. Do we see why that's more stabilized? Having this extra resonance contributor in our middle. This one's stabilized by hyperconjugation with the two groups nearby, but this one's stabilized because of this resonance contributor, the bromine carrying part of that positive charge. Okay. So that makes this the much more favored cation and therefore the more the more common product. Okay. All right, so mechanistically, it's the same as adding it across alkenes, and we still get Markovnikov's products. Okay. So what if you were just adding halogens across it? Well, we had that mechanism of halogens, right? Where it would sit on the top and then it would have to have the other one come in anti. What we see is, in the case of adding one equivalent across there, we do see a majority of the product being that anti addition, or in this case, the E configuration, because the bromine is the trans configuration. The bromines are the highest priority, therefore they're opposite each other, giving us that anti addition as our major product. It's not the only product, because there is some little rearrangement that happens, but it is the predominant product. However, if you add a second equivalent of your halogen to it, stereochemistry doesn't matter, because you end up with two sets of geminal halogens on adjacent carbons. So we end up with basically the tetrahalo compound. We're adding chlorine across the first double bond, chlorine across the second double bond, and you're done. Questions on additions of halogens. Okay, so it's the exact same mechanism. You just have to know whether you're adding one equivalent or two equivalents. All right. So let's move to reductions. When we had reductions, that was a syn addition of hydrogen, because we had the alkene coming and sitting on the surface and transferring two hydrogens at the same time, or very close to the same time, and it gave us syn addition. However, when we look at alkynes, the alkyne, the first double bond would come and do that, but now the second, the alkene that it formed is just as reactive as the alkyne, and therefore gets reduced down to the hydrocarbon. So if you ever see a question on homework that you had a palladium on carbon, or catalytic hydrogenation of an alkyne, and you don't say anything else about it, it's going to reduce it all the way down to the alkane. Okay. The only way to stop it at the alkene is to poison the catalyst, make the catalyst less reactive to alkenes. It's still reactive to alkynes because they're more reactive, but it's less reactive to alkenes. And the way we poison the catalyst is we use a compound called quinoline, and this would actually be lead, it's Pb, lead and barium sulfate, okay? And we call this Lindlar's catalyst because we've taken the activity down a notch. When we do that, we still get syn addition because we're still doing it at the surface, but it stops at the alkene. It's the only way to generate our alkene. Again, without poisoning the catalyst, this alkene's just as reactive as the alkyne, and we get the alkane. By adding this lead and barium sulfate, we stop at this, the syn addition product, okay? So that's always gonna give us this cis alkene, or the Z alkene. What if you want the other one? If you want the other one, you have to go through a different mechanism and a different way to reduce it, okay? So let's say we wanted the trans alkene instead. We can't get the trans alkene with a surface hydrogenation because it adds to the same sign. So let's change the mechanism up a bit, okay? So if we change the reaction to what we call the dissolving metal reduction, we've changed the mechanism, and this allows us to get a trans alkene from an alkyne, okay? So that trans alkene we can get from that alkyne is done through a carbanion, a negative charge on carbon, okay? So how does it work, okay? Well, as the name suggests, we have a bit of metal in the reaction. It happens to be sodium. And so you end up actually putting these little spheres of sodium in the solution, and you stir it around, and slowly those little spheres of sodium dissolve. So here's what's happening. That sodium is going to lose an electron, become sodium plus 1. That electron is going to add to the triple bond. When it does that, we have a radical addition, a single electron addition here, that splits one of the double bonds with an electron moving to each one, and we end up with this trans radical anion. Slides are wrong, it says cation, it's an anion. So we have an anion here and a radical on this side, okay? So, and notice that this intermediate has the two R groups and their trans configuration, okay? So the two R groups are going to be in that trans configuration because that's the most thermodynamically stable form of that. Okay. Now it has to go through some other process, okay? So now that we have this anion here, it acts as a base and deprotonates the solvent, which just happens to be ammonia, okay? When it does that, we end up with sodium amide as a byproduct and a radical, an alkenyl radical, okay? So what's going to happen next? Well, we need another addition of sodium to turn that into an anion. So we're going to transfer one electron over, making an anion again. That anion is now a very strong base. It removes a proton from our ammonia again, giving us our trans alkene. But notice that once we formed this first trans radical anion species, those R groups don't move. They stay in that trans configuration through every step of the mechanism. And when it stays trans through that, we end up with the trans alkene at the end. Okay, so if you want the cis alkene, Lindlar's poison catalyst. If you want the trans alkene, dissolving metal reduction, sodium metal in ammonia. And because they have two different mechanisms, we specifically get two different products. All right, questions on those, reductions of alkynes? No? All right. So we've done addition of an acid, addition of halogens, we've done reduction. Now let's do hydration. We're gonna add water across that triple bond, okay? So when we add water across the triple bond, we have to use a little bit of a catalyst here. In this case, we use mercury sulfate as our catalyst. And what's gonna happen is we're gonna add one equivalent of water across that double bond. And when we do that, and it's, by the way, it adds Markovnikovs, just like the other mechanism. We're gonna do a Markovnikovs addition of water across the double bond, okay? What does that do? So if we just add water across that double bond, we're gonna end up with, water across the triple bond. We're gonna end up with an alcohol, a hydrogen, and we still have one pi bond left, so we have a double bond. When we do that, we create what's called an enol, right? It's an alkene and an alcohol at the same time. So when we did nomenclature, we said enol was when you had an alcohol and alkene. However, enols aren't very stable, and under acid or base, they can rearrange. And when they rearrange, they form carbonyl compounds, okay? So it's either gonna be an aldehyde or a ketone, but it's gonna be a carbonyl compound, okay? Because it's more stable in this form here than in this form here. And I'm gonna go show you the mechanism of how it transfers back and forth, okay? So knowing that it goes to some kind of carbonyl compound, when we have an alkyne, we're going to add it in a Markovnikovs fashion. So in the case of the terminal alkyne, we're gonna end up with the methyl ketone. The hydrogen's gonna go on the end with the hydrogen, and the OH is gonna add to the second carbon, and then it's gonna rearrange to give us our ketone. Now in the middle of an alkyne, you might not see where it goes, but it does actually do a Markovnikovs addition, giving you a ketone as well. Okay, so what does that seem to look like? Well, this seems to look like the regular addition of water, but mercury's help mediating it. Mercury is less electrophilic than carbon, and so it's going to carry more of a positive charge. And your water is going to end up being a weak nucleophile and attacking anti to the mercury cation three-membered ring on the top. Okay. Well, after it does that, that mercury can then go ahead and be reduced off, displaced by hydronium ion or a positive hydrogen to give us our enol. Okay. Now that enol is going to reorder. And I said it's either acid or base catalyzed. So let's look at that mechanism of the rearrangement first, okay? So there's a thing called Enol Tautomerism, okay? Which means any ketone with a hydrogen adjacent to the carbonyl can undergo a reversible reaction to form. Part of the time it's going to be the enol, but most of the time it's going to be the ketone or the carbonyl compound because it's more stable. So they're moving something big and heavy out of the elevator right now. Okay. So if we start with the enol, because this is where we just added water across our triple bond, what can happen is that the alkene can be protonated by acid to give us this intermediate where we have a cation on the carbon with the oxygen on it, and the hydrogen is transferred to that terminal carbon, okay? Then what will happen is, of course, our electrons will kick in and give us our intermediate with our protonated ketone, and then by removing that proton, we end up with the ketone form. So that's how we do it acid catalyzed, but it'll also do it base catalyzed too. By acting as a base, it can deprotonate that alcohol. And then when it kicks in, it'll kick out here, giving us an anion on our carbon here. And then that carbon will act as a base and deprotonate something and give us our keto form as well. Notice we can form aldehydes or ketones from this, depending on where that alcohol is. The alcohol is terminal on this one, and it'll end up giving us the ketone. But remember, this is a Markovnikov's addition reaction. So you're always going to see the OH on the more substituted carbon, which means your carbonyl is going to be on your more substituted carbon. Right. Questions about the addition of water across a triple bond? Notice only one equivalent adds. You know, we always end up with at least one with that ketone there, and that ketone is stable to that hydrolysis. All right, moving to the next thing. So now we've done hydration. What else can we do? Oh, oxyboration, hydroboration, oxidation, deboronation, right? When we have alkynes, to make sure the reaction stops where we want it to, we only use boronating agents with a single hydrogen to transfer. Okay, remember when we did hydroboration oxidation reactions, we used borane, which was boron with 3 hydrogens. And all 3 of those hydrogens reacted with an alkene, and then we had to oxidize them off to get our alcohols. When we do reactions with alkynes, we use very specific boronating reagents that only have 1 hydrogen to react, okay? Now, it's going to react exactly the same way it did in borane. It's going to react anti-Markovnikov's, giving us our boron on our least substituted carbon, partially to sterics, partially to electronics. And so when we get that, we're going to end up with this stable compound, this vinyl borane, where the boron's on the least substituted side, okay? Now, when we do the oxidation step, we're going to end up with an enol again. When we end up with an enol, it's going to rearrange to its more stable form. And in this case, we're always going to get an aldehyde, okay? In the other case, if you have any alkyne, you're always going to end up with a ketone because you're going to do a Markovnikov's addition. Your OH is on the more substituted carbon. So doing just acid catalyzed hydrolysis of an alkyne always yields a ketone. Using the boronating reagent, boron hydroboration oxidation, you get the aldehyde. Okay, so that's very important to note that just like in the case of wanting a secondary alcohol or a primary alcohol, if you want the ketone, you have to do the addition across the alkyne with water. If you want the aldehyde, you have to use the hydroboration oxidation mechanism. Okay. Now, again, all of these can be any type of boronating reagents as long as there's just 1 hydrogen. And these are the most common, the dicyclo, the isoamyl, and then this borocyclononane, or BBN. Questions on that? Just like in the alkenes, it's site selective. You can choose exactly where you want your functional group by choosing your reagent. Okay, so now let's do an oxidation here. Luckily, oxidation, if we use ozonation, it gives us the exact same product. It clips the triple bond and turns it into 2 carboxylic acids. Okay, so that reaction is identical. Instead of just clipping the double bond, it's going to clip the triple bond and give us that carboxylic acids. And again, it's the same mechanism we used before. Now, when we did permanganate under basic conditions, we also clipped that double bond and gave ketones and aldehydes. Gave ketones and carboxylic acids. However, in an alkyne, if we do it in neutral pH, pH 7, we actually can do some really cool different chemistry. The first thing it'll do is it'll add 2 hydroxides to 1 double bond, and then it's going to add 2 hydroxides to the second double bond, giving us a tetrahydroxy compound. But this tetrahydroxy compound is not very stable and will lose water off one side and water off the other side and give us a diketone. Okay, so that's unique. That's the only time we've ever formed a diketone, and this is how we do it. We're going to take permanganate and add it in neutral conditions, pH 7. We're going to add 2 hydroxys, and instead of clipping it like we did when we had that basic conditions, it's going to give us a diketone. Okay, if you have an internal alkyne. If you have a hydrogen at the end, you actually are going to be oxidizing that down a little bit, and you're going to end up with a ketone and a carboxylic acid, or a keto acid. Okay, again, that's 2 different functional groups during the same reaction. So that's a very important conversion of material. Questions on that? Okay. All right, no guest speaker yet. All right, so let's continue. Okay, so when we use it neutral, we get these cool diketones and these keto acids. What happens when we use it in base? When we use it in base, we do exactly what we did with the alkenes. We clip them off, we clip that triple bond and turn it into carboxylic acids. Okay, so it's the same. And if it's an internal alkyne, you end up with 2 different carboxylic acids. If it's an alkyne at the end, a terminal alkyne, you're going to end up with CO2 and 1 carboxylic acid. This will break down into carboxylate ion, which breaks down to CO2. So you only have 1 product with this. Now, if you have a symmetrical alkyne, you'll only end up with 1 product too, but an unsymmetrical internal alkyne, you get 2 different carboxylic acids, using that same mechanism we did with the alkenes. All right, questions on that? Okay, so notice a lot of the same reactions are the same, but there are some unique differences. So you need to make notes of the differences, like neutral potassium permanganate and that Enol Tautomerism found in the oxidations. All right, so that is how alkynes are different than alkenes. Okay, so is there any questions about any of the alkene mechanisms or any of the alkyne mechanisms before we move on to chapter 9, which is Nmr spectroscopy and mass spec? All right, let me pull up the chapter 9, Nmr. Okay, so IR spectroscopy, we looked at it and we looked at individual bonds and bond types, and we were able to see the individual types of bonds. Okay, with NMR spectroscopy, we're going to get connectivity. What's next to what? Okay, so we're adding something to our toolbox for identifying. With the IR, we could only say whether or not this type of bond was found in there. We couldn't give the exact functional group or the exact structure. So NMR, we're starting to get more and more specific, and we can see new things. Okay, just like the name, well, I mean, let me tell you what the name means. The NMR means nuclear magnetic resonance spectroscopy. So that means we're going to be looking at the nucleus of individual atoms, okay? So in IR, we were looking at the bonds between two atoms, and we were using infrared radiation, which was part of the electromagnetic spectrum, okay? In the case of NMR, nuclear magnetic resonance spectroscopy, we're actually going to take advantage of the fact that the nucleus of each atom, because they're spinning quickly, they end up having a pole, just like a planet or the Earth, because it's spinning in an internal, excuse me. When we have something spinning, it generates a magnetic pole, okay? Now, these nuclei are kind of insulated from each other by all those electrons, right? So they don't really line up. They're just randomly assigned, randomly pointing in any direction. However, if you take these nuclei, these nucleuses of all these atoms here, and put it in a strong magnetic field, then they will line up with that magnetic field, either in line with the magnetic field, which is the lower energy way to do it, or anti or opposite lined. So this is anti-parallel, is where they're pointing in the opposite direction of the applied field. And when they're pointed in the same direction as the applied field, we call that parallel, okay? So there's going to be some random number of ones that are anti-parallel, but most of them are going to be parallel with this magnetic field. Okay. So again, in IR spectroscopy, you're using a really low energy wavelength of light to measure the difference between those two atoms here. In this case, we're going to use radio frequencies, and we're going to pulse the radio frequency into this. And when we do that, we are going to be able to take some of these molecules that are in the parallel configuration, and we're going to flip them upside down, okay? So what we've done is we've hit it with radio waves, and we turned it into this excited state, okay? Now, we are going to wait and listen for them to emit energy as they relax back down to their regular state, okay? So the time it takes for these things to relax is what we're going to see on the x-axis of our NMR. That's our shift that we're going to see, okay? It's the time it takes for these things to relax back down into their parallel orientation, okay? So we're still using electromagnetic radiation. We're aligning everything in a magnetic field. We're hitting it with radio waves, and we're listening for when they relax back down to their normal state. Okay. So when we talk about NMR, we have to talk about specific nuclei. In fact, if you look at it, all of the NMR active nuclei are those that are odd in mass, okay? There has to be a difference between the number of protons and neutrons. There has to be an odd number of protons and neutrons to have it be NMR active. So the most common of these is what we call proton NMR, or hydrogen. Hydrogen 1 is the most common isotope of hydrogen. There's also hydrogen 2 and hydrogen 3. Hydrogen 2 is NMR inactive. It is invisible to NMR. In fact, we use hydrogen 2, or deuterium, as the solvent for these things, for these experiments, because it's completely invisible to NMR. So we have to have an odd number of things, and you're going to see this because we're going to do hydrogen, which we call proton NMR, and then we're going to do carbon, but we're going to use a specific isotope of carbon called carbon-13. So that having that odd number of protons and neutrons is important to make these things IR active. Okay, so now that we know we have proton NMR means hydrogen NMR, when we have hydrogen NMR, there's 4 important things to note, okay? We need to look for the number of different types of signals we have. The number of signals we have tells us the different types of hydrogens we have in our compound. The second thing we look for is the intensity, or the number of hydrogens in each peak. So you can tell the relative intensity between this peak and that peak and say there's 3 hydrogens here and 2 hydrogens here. That helps us identify our product. Okay. Then the position of the signals, where they shift up and down on that x-axis. That's the shift or position of signals. And then the last thing is what we call spin-spin coupling or spin-spin splitting. What we're going to see is if you have hydrogens nearby, they're going to split your signal, and the number of times it split tells you how many hydrogens are nearby. So that's going to help you think, oh, I have exactly this many hydrogens here, I have exactly this many hydrogens here, I have exactly this many hydrogens here. So it helps elucidate your comment. So we knew 4 things that we want to look at in every single proton NMR. And so if you think of it backwards, it's spin. So spin proton NMR. It's cute. Okay, so am I bet I did. Okay, let me switch to this one here because I did this one too. I've already lectured on this. Why is there notes on it? Okay. Okay. Did I lecture on this already? Because there's notes on here. No? Okay. That's weird. Okay. Oh, I copied it after I made notes. Oh, poodles. Sorry about that. All right, let me erase. Okay, good. Okay, so what a normal NMR spectrum looks like is something like this. We're going to look for those 4 things. The first thing is the number of different types of peaks we have. So in this case here, we always look for this little peak down here, right here. This is our 0 point. It's an internal standard. We always include it so we know exactly where 0 is. And I'll tell you a little bit more about that later. It's what we call tetramethylsilane. Okay. And by convention, we say that is always 0. And so the number of peaks above this internal standard is the number of peaks. Okay. So in this case here, we have 1 set of peaks here and 1 set of peaks here. Okay. So that means we have 2 different types of hydrogens, and I'll talk about equivalent hydrogens in a minute. So that's number 1, our number of types of peaks. Okay. The second thing is intensity, and the relative intensity is how big they are here. However, because our peaks can be split, what we actually do is we measure the area underneath all of the peaks. And when we do this, it's called integration. And if we look at this integration to that integration, what we'll see is that this is going to be an equivalent of 2 to 3. And so we'll know we have 2 hydrogens on this peak and 3 hydrogens on that peak. So that's intensity. But again, it's the integration of the area under all the peaks of that peak type. Number 3 is position or shift. Notice we started at 0 here with our thing. And so we have 1 peak that shifted at about 1.75 and another peak that shifted at about 3.5. What that means is that they have different electronic environments. The further up you are, the further away from 0 you are, the more you're interacting with some kind of, we'll see that it's either a nucleophilic atom or a double bond or a carbonyl. Okay, so that position tells you what's your nearby. And then the last thing is the splitting. Notice that, you know, if we looked at that, it's like, well, we should get 1 peak here and 1 peak here. And technically, we do get 1 peak for each of these, 1 peak here and 1 peak here. However, because of spin-spin coupling or spin-spin splitting, this peak is split into 4, and we call that a quartet, and this peak is split into 3, okay? That splitting tells us something about what's nearby the peak we're looking at, okay? And I'm gonna tell you how to elucidate that as well. Okay, so those are the 4 things we look for in every single NMR, okay? So let's start talking about number of signals. So number of signals is determined by the number of different types of hydrogen. Now, by different types of hydrogen, I want to say that they are unique hydrogens that have the same electronic stuff nearby, okay? So if they have the same bond structures, then they might be equivalent to each other. So let me tell you what I mean by that, okay? So let's look at this. So in this right here, you'll say, well, okay, we have 2 different types of hydrogens. We have 2 different peaks. We have this one and this one. It's 2 different peaks. Well, let's take a look. We have this hydrogen that's bonded to a carbon that's bonded to two hydrogens, that's bonded to an oxygen that's bonded to a carbon, okay? So if we just look at the connectivity, we have a hydrogen bonded to a carbon with two hydrogens, bonded to that. And guess, in all of these hydrogens are all bonded to the same carbon. So we have three equivalent hydrogens that are on that methyl group. But if we do the same analysis over here, we have a hydrogen bonded to a carbon with two hydrogens, bonded to an oxygen, bonded to a carbon. Electronically, they're identical, okay? Which means that these three hydrogens on this side are going to be chemically equivalent, or NMR equivalent, to these three hydrogens on the other side, meaning we're going to get one signal. Okay? See how they are, if you go through the connections, they're identical, right? Chemically. Now, let me show you something that's not equivalent so you get the hang of it here. In this case here, we have a CH3 that's bonded to a carbon, okay? But let's look at this one here. We have a CH2, okay, that's already different. And then it's bonded to a chlorine on one side and a carbon on the other, okay? So these two hydrogens are not equivalent to these three hydrogens. So we should have two peaks. Because both of these hydrogens are equivalent to each other, but they're not equivalent to the CH3. Those three hydrogens on the CH3 are equivalent to each other, but they're not equivalent to the CH2s. So we get two signals. Okay, so let's take it off of a notch here. So we have a CH3 and we have a CH3. All right, those are equivalent, right? No. We have a CH3 bonded to an oxygen. We have a CH3 bonded to a CH2. That makes these two CH3s different. Okay, so they each have their own unique signal. So we get one signal for this one. We get one signal for that one. And since the CH2 is different than either one of those, we get a third signal for the CH2s. So we have three different types of hydrogen. Does that make sense? Okay, you're looking for the connections. They have to be connected completely identically to be even considered equivalent. And then you have to look at where they are in space. Now, why do I say that? Because when you have things that are constrained in space, like alkenes or cycloalkanes, you'll start to see that in space makes things different. And it's important for you to draw your configuration such that you can see where the hydrogens are, not this structure here. You can't see where the hydrogens are. But here you can see that you have this hydrogen's different than all the other ones because it's bonded to the one with the chlorine. These hydrogens are equivalent and they are influenced by being next to this chlorine. But that means these hydrogens are actually now different because they're only adjacent to a hydrogen. So by drawing it this way, we see we have three types of hydrogens in this small little molecule, okay? We see that same thing in alkenes, okay? So if we draw our alkene out such that we can see the spatial orientation of where the hydrogens are, you will see that this hydrogen here is close to this chlorine, which makes it not equivalent to the hydrogen down here. This hydrogen, even though they're on the same carbon, through space, this hydrogen doesn't see chlorine, that one does. So that means that's a different chlorine, that's a different hydrogen. And that means this is a different hydrogen because it's on the same carbon with the chlorine. So even though we have three hydrogens on just this alkene here, we have three unique types of signals. So we should see three peaks in the NMR. Does that make sense? Okay, you're looking at not only connection, but through space. So your stereochemistry gives it that. Okay. So let's do a few tests for equivalency. Okay, so let's look at this first one up here, and I'm gonna draw it big as soon as I erase. Okay, I really wanna drive home this equivalency because this is if you get this right, you're going to have a very much easier time with NMR. Okay, so let's look at this one right here. Okay, now before we start, let's draw that last hydrogen. That last hydrogen happens to be over here. And this is a CH3 group, and these are CH3s at the outside edge too. Okay, so here we're going to start to look for symmetry. Okay, now luckily I've already drawn the mirror plane here, which means that we have number one, no hydrogens here, no hydrogens here. So we're not going to get a signal for that. Okay, so because we have no hydrogen, so we're good there. And I'm going to say that these hydrogens are identical to these hydrogens because if we look at their connectivity, they're the same. It's a CH3 connected to a carbonyl connected to a tertiary carbon, CH3 connected to a carbonyl connected to a tertiary carbon, and they actually meet at the same center. So those two CH3 groups are identical because of symmetry. Okay. Now, is this CH3 group the same as the other two? Well, let's look. We have a CH3 going to a tertiary carbon. There is no carbonyl there, so it's not equivalent to either one of these, which means it's a unique signal. Okay, and let's look at that last hydrogen. There's nothing else that's just a single hydrogen on carbon, so it must be a unique signal. So we're going to have 3 signals for this molecule. Okay. Questions on that? Okay, we're right here at 1:20. So we have till 1:50. So we have 30 minutes left, right? Okay.
Can you explain again why it's 3 and not 2?
Okay. So do we agree that these 2 outside ones are identical because of symmetry? Okay. So if we look at the connection between this one right here, if it was to be like this, it would have to be attached to a carbonyl, attached to a carbon. This CH3 is attached to a carbon with no carbonyl. So immediately it has a different connection. So that makes this methyl group different than that methyl group. Do we see that? Okay. Now, we had to draw in our last hydrogen here. Okay. This hydrogen is not like any other hydrogen. It's the only one that's on a carbon bonded to 2 carbonyls and bonded to a methyl group. So it's different. So that's our 3rd signal, is our unique hydrogen here. Our 2nd signal is our methyl group here, and our 1st signal is our 2 identical methyl groups. Does that
makes more sense now. Thank you.
Okay, so let's take those hydrogens in space and look at them again. How many equivalent hydrogens do we have in this? How many peaks would we see for this compound? Just 1. Because this hydrogen is the same as this hydrogen, is the same as this hydrogen, is the same as that hydrogen. So we're going to get 1 peak. See how they're all bonded to the same carbon, and they're all bonded to a carbon with 3 other hydrogens? Bonded to a carbon with 3 hydrogens, bonded to a carbon with 3 hydrogens. So they're all identical, so we get 1 peak. All right, let's make it harder. No, let's take what we just learned in that last one and do it again, okay? How many peaks do we get for this compound? Well, let's break it down. We have this carbon right here. So we have 3 hydrogens bonded to 1 carbon, bonded to a carbon. All right, so that's going to give us a unique signal here. Okay, let's look at the other side. We have a hydrogen, and we have 3 hydrogens bonded to a carbon, bonded to a carbon. Ooh. Let's look at this carbon. This carbon has 3 hydrogens on it. This carbon has 3 hydrogens on it. That means that those 2 carbons have the exact same connectivity with all the different hydrogens, right? These 3 hydrogens have the same connectivity that these 3 hydrogens see. So we have 1 and only 1 signal. These are equivalent to these because of connections. Therefore, we have one signal. Okay. All right. Let's do 3 more. I really want to drive this home. Once you start seeing equivalent hydrogens, you'll start really getting the number of peaks you'll see. Now, I said before that because these have this through space interaction with chlorine, they have a unique signal compared with these, because these only have an interaction with hydrogen. Okay. Otherwise, you would think they would be almost identical because of where they're focusing. And if you look at their connection going all the way around, it's all the same. But the stereochemistry, having this locked in position, makes it different. And then, of course, this is a single hydrogen, so that already makes it different, and it's bonded to a carbon with a chlorine on it, which makes it unique. So we have 3 signals for that one. Okay. Here we go. We're going to look at that going around the circle again. Okay. So in this one right here, I think the 2 hydrogens that are on these chlorines are going to be the same, because if you look at the connections either way, both of these have the same connections either way. So this is going to give rise to 1 signal. Okay, in fact, I'm just going to draw a circle. This hydrogen and this hydrogen are the same. They're going to give 1 signal. Okay. All right, let's look at these hydrogens here. So we have a chlorine in that direction and a CH2 in that direction. And we have, if we looked at this right here, we have a CH2 in that direction and a CH2 in that direction. So that means these 2 are different from each other, because we saw a chlorine this direction and we only saw a CH2 that direction. So that means we have to have at least 2 different signals there, right? So I'm going to say that that red hydrogen is different than that green hydrogen. Let's look at the other side. If we look at this, if we look at this hydrogen, we have a chlorine that way and a CH2 that way, but that's exactly the same as this one. So I think those 2 are going to give an equivalent peak. And then if we look at this one, we have a CH2 this way, CH2 that way, CH2 this way, CH2 that way. So these 2 are going to give rise to a single peak. And because the way these are configured, I think that we're going to end up with a total of 3 peaks for this one. And if we think about it, that's going to be going back and forth between the 2 different chair configurations, because we have them both on the same side. So that should be it. And then again, we already did this one here, but this one's different because of its through space interaction. This one's different because it's bonded to the carbon of the chlorine. And this one's different because it only sees hydrogens through space. So that gives rise to 3 different peaks. All right, does that start to make sense now? You're starting to look for things that have different connectivity and different spatial orientations to give you your uniqueness. Every time you draw a circle of different types of hydrogens, you should get a peak in the NMR. It might be a single peak or it might be a split peak. We don't know that yet, but you're going to get a peak for that in the NMR. Okay, the second thing we want to do is talk about intensity, okay? And it's not as simple as saying, oh, this peak is 3 times taller than that peak, or this peak is 5 times taller than that peak. We actually have to take the entire area under the curve, because the peaks can be broad or the peaks can be whatever. And so what the number is going to give you is it's going to give you some relative number, okay? But the ratio between the 2 is going to be the number of hydrogens on each of those types of peaks, okay? So in this case here, we have these 3 CH2s are different than this CH3 because this one's bonded to an oxygen and these are bonded to a carbon. So that makes them 2 different peaks, okay? This has 9 hydrogens on it and this has 3 hydrogens on it. So the area under this curve is going to be 3 times more than the area under this curve. And so if we did the relative ratio of 333 divided that by 1,000, you'd see that the 9 hydrogens are represented by that area and the 3 are represented by that. Sometimes you'll just have integrations and it'll be like 1, 2, 3. Sometimes they'll be like this, where it's the the raw number and you have to divide them to figure out how many peaks are in, how many hydrogens are in each peak. Okay, question on intensity. So it's going to be a relative ratio between peaks, the area under that curve. Okay, now the hardest one, no, actually, it's a little hard when you first start, but it's really not that hard. What we're going to do is we're going to talk about chemical shift or position. Okay, so when we talk about position, we have to do a couple words. We have to use the word downfield, which is further away from zero, okay, which makes them easier to resonate, which makes them slower to relax. And then we have upfield. Those are harder to resonate, which means they are faster to relax, okay? And for our convention, we have this compound here, tetramethylsilane, as our 0 point. And if we look at this, all four of these methyl groups are identical, and they're bonded to silicon. Silicon's a more electronegative atom, a less electronegative atom than carbon, and therefore it's going to be further upfield from any carbon-carbon type bonding. So we call that 0, okay? And everything else, every other methyl group or whatever bonded to another carbon is going to be above that or downfield from that. So another interesting thing is that we also, instead of just using the frequency that it took, the time it took to relax, we actually scale it. So no matter what type of NMR we have, we're going to end up with the exact same number. And the way we do that is we take the observed frequency and we divide it by the frequency of the machine. So your machine can be a 60 megahertz NMR. That's the frequency you're pulsing with. A 300 megahertz NMR, that's the frequency you're pulsing with. And because you're pulsing with a higher frequency, you're going to get a bigger shift in the spectrum. And it would be very confusing saying, well, you know, hey, I got 200 hertz, you got 900 hertz. Are they the same thing? Well, luckily, by dividing the observed peak by the frequency of the NMR, we end up with what we call parts per million, or shift in ppm. So it doesn't matter what type of NMR you use, your shifts are always going to be in the same place. And we're going to do them by ppm. And they typically go from 0 to 15 in Proton Nmr. Okay? So questions on shift, what shift is. Okay. So what we see is that as we have the individual hydrogens are aligned in that magnetic field, its ability to relax is changed by how close it is to an electropositive or electronegative atom. And so when it's next to something that can hide some of that magnetic field, it's called shielded. It's shielding its hydrogen from that magnetic field. If you can't shield because you don't have enough electron density in that area, or you're pulling electron density away, you become de-shielded. You have less electrons to repel that magnetic field, and therefore you get shifted downfield. So imagine anything that's going to help pull electron density away from your hydrogen is going to shift you downfield or to higher ppms. Okay, so upfield is closer to 0, downfield is further away from 0. Let's figure out, just by looking at the chemical structure, if we can predict upfield versus downfield. Okay. So let's see, we have 2 different methyl groups and they're different, okay? And we have the first one, it's next to a carbonyl, okay? And so that means that carbonyl, it has a different hybridization than if it was a CH2 group. So that different hybridization is going to make it be able to pull some electron density away through inductive effect, shifting your protons away from 0 slightly. Okay, so If it was just a straight chain hydrocarbon, it'd be here at right around 1. Because of this carbonyl, it's pulling electron density away inductively, and it shifted downfield. It shifted downfield, further away from 0. Okay. Now, by resonance, this oxygen here is going to be more electronegative than the carbon, and is going to inductively pull even more electron density away than the carbonyl itself, and is therefore shifted downfield as well. In fact, it shifted further downfield than the carbonyl would. Okay, so these are inductive effects at allowing you to see how much electron density is around these unique types of hydrogens. Okay. So downfield is higher ppm numbers, upfield is lower ppm numbers. So imagine anything that has a more electronegative atom, or as we start to see double bonds and triple bonds, that's going to shift things further downfield. Okay, so let's draw some conclusions about this inductive effect and where the different functional groups would show. Okay, so everything that's just bonded to carbon is going to be our closest to 0, right? So our hydrocarbons and our CH2s next to CH3s next to CH2s, anything that's like a long chain hydrocarbon is going to be in this 0 to 2 range, because carbons are bonded to carbons. They're not really inductively pulling anything away. And so they're going to stay right in that lower regime, that beginning time frame of relaxation. Now, attach a slightly more electronegative group to it, and it shifts up. Aromatic ring, a nitrogen, a sulfur, or a carbonyl, or a double bond. These are slightly electron withdrawing, and it shifts it up to the next level between 2 and 3. Okay. However, if it's directly bonded to an oxygen or a halogen, that shifts it up again. Those are more electronegative atoms. Nitrogen's less electronegative than oxygen, so these are the more electronegatives. It shifts them up even higher. Now, these are electronegative atoms, but they're way up here, and they have a broad range. The reason they have a broad range is both of those compounds can hydrogen bond. The number of hydrogen bonds and the type of hydrogen bonding can shift that peak really around quite a bit. And sometimes it can even broaden the peaks out. Okay, so it's bonded to an electronegative atom, but hydrogen bonding is what causes it has such a wide range. Okay, now the next kind of a hydrogen we have is a Sp2 hybridized hydrogen. And it's, the double bond is the one that's doing a lot of the work, and it's changed its hybridization, so it has more S character, so it's shifted up to the next range. Aromatic rings, because of resonance, shifted up even higher. Then the two highest ones are aldehydes and carboxylic acid protons, because they're directly bonded to carbonyls, or they are very acidic because of resonance. So that's why these two are shifted higher. So there's an argument for where these shifts are as you get more and more deshielded, more and more having an electronegative intensity effect, the further downfield they go. Okay, so more hydrocarbon-like, closer to 0, a little bit of electronegativity next, directly bonded to an electronegative atom next, directly bonded to a double bond, directly bonded to an aromatic ring, directly bonded to a carbonyl, and the only one that does that is aldehyde, and then directly bonded to a carboxylic acid, continuously shifting downfield as we go. Does that trend make sense? Okay. As you steal more electron density away from it, it moves further downfield. All right, so the last thing we need to do is we need to talk about splitting. Some people think this is the hardest, but I think it's not as hard as you think it is. We just need to follow 3 rules. Okay, number 1, equivalent protons don't split each other. Okay, so let's look at a compound like CH3, CH2, Br. Okay, that means these 2 hydrogens are equivalent hydrogens, and they're going to give a single peak no matter what. Okay, so that's our first rule. These 2 hydrogens are 1 peak. Okay, Second rule, you look for the number of non-equivalent hydrogens 3 bonds or less away from this peak. Okay, so let's redraw this to be a carbon with a hydrogen, 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 carbon, hydrogen, hydrogen, and a bromine. Okay, so the first thing we saw, rule 1, is these give 1 peak. Okay, now we look for the number of hydrogens that are within 3 bonds of that group. Okay, so let's look at that. We have this hydrogen here, so we have 1, 2, 3. So this hydrogen counts. We have 1, 2, 3. This hydrogen counts. 1, 2, 3. This hydrogen. Whoa, where'd it go? Okay, hang on. Touch the side of my iPad again. Okay. All right, so let's go back to that. So this, you know, okay. So this counts right here. Okay. Why is it moving? It's supposed to be writing, right? Okay. All right. So if this hydrogen counts, and this hydrogen counts, and that hydrogen counts, we have a total of 3. Well, it's not letting me write for some reason. Here, let me close it and open it again. Sorry if you're getting seasick from this. Okay, let's see if I can write now. Yes, all right, great. All right, so I'm gonna go back to my explanation here real quick. Okay, all right, so we have our C with our H here and our bromine. And then we have our C with our H, and H. Okay, and these 2 hydrogens, by rule number 1, have 1 peak. Then we need to count how many hydrogens are within 3 bonds of that hydrogen. So we go 1, 2, 3. We have 1 hydrogen. 1, 2, 3 bonds. We have 2 hydrogens. 1, 2, 3 bonds. We have 3 hydrogens. Okay, so we have 3 non-equivalent hydrogens. So that's our N, the number of non-equivalent hydrogens, plus our 1 peak for the hydrogens we already had, is our N plus 1 rule. Okay, so that means that we're going to have 1 peak for this, and then each of these hydrogens is going to split that peak 1 more time. So we're going to have 3 plus 1 is equal to 4 peaks. Okay, so the non-equivalent, the equivalent hydrogens are a single peak. All of the hydrogens within 3 bonds split it again. So that's our N, and that's our 3, and that gives us a total of 4 peaks. And then splitting is only observed for protons on adjacent carbons, okay? Or non-equivalent protons on the same carbon. Remember, when we had our alkene that was mono-substituted here, each of these is unique. Each of these hydrogens was unique. So that means this is going to be split by this one and this one. This one's going to be split by that one and that one. This one's going to be split by that one and that one, because they're all within 3 bonds. So they are observed on non-equivalent protons of the same carbon or adjacent carbons. So let's play with this rule, okay? Okay. So let's look at this example here. And we have R groups, okay? So this, we're going to say these R groups are different than these R groups here, so they're going to be different hydrogens. This peak gets 1 for itself, and it has 1 hydrogen, so N is equal to 1. So you have 1 plus 1 equals to 2. So this is going to have 2 peaks, okay? This red one is going to have its own unique peak, plus it's 1, 2, 3 bonds from 1 hydrogen. So that's N is equal to 1. And so your total is 2. This is going to be split into 2 peaks. Okay. And the way it ends up doing it is the peak itself is going to be at a certain frequency. Then when you split it, you're actually going to split half of it up and half of it down. And so the peak actually splits symmetrically, and you end up with them, basically your set of peaks being aligned with the center of if it was not split at all. So in the case of these hydrogens here, we end up with 2 peaks. 2 peaks is called a doublet. 1 peak is a singlet, 2 peaks is a doublet, 3 peaks is a triplet, etc. So let's go to rule 2 and look at this additions here. So now by adding a single hydrogen to this, we're going to change our n+1s, okay? So if we look at this hydrogen here, that gives us 1 peak for that, but we have a total of 1, 2 hydrogens. So this is going to be 1 plus our n is equal to 2, 3. So that means that this hydrogen is going to be split into 3 peaks, or a triplet. Okay. If we look at these 2 hydrogens, they are magnetically equivalent. They are identical. So this is 1 peak. And there's only 1 hydrogen next to it. So that's our n is equal to 1, which means that peak is going to be split into a doublet. So this 1 hydrogen is going to be a triplet. These 2 hydrogens are going to be a doublet because of the hydrogens within 3 bonds of the magnetically equivalent hydrogens. Okay, so there's some very common patterns we're going to be seeing. If you have no hydrogens within 3 bonds of your unique hydrogen, it doesn't split. You have 1 peak and it's going to give you a singlet, okay? If you have 1 hydrogen next to it, you still have a total of 2 peaks because you have the peak itself plus the neighboring hydrogens. And the relative intensity is going to be a doublet where they're equal heights. You're going to have a doublet, 2 peaks, and they're going to be equal heights. Okay. If you have 2 hydrogens, that's going to give you a total of 3 peaks, but it's going to look like this. It's going to be 1, 2, 1. And it's going to be a triplet. If you have 4, it's going to be 1, 3, 3, 1. So they have these unique patterns. You can tell by the number of peaks and their relative intensities how many nearby hydrogens you see. And then once you can have a total of 9 peaks, which would be a non-net. So what does that look like? Okay. Okay. What does it look like when we pull it all together? Okay. So let's predict the number of peaks that we'll have for each of these types of hydrogens in propane. Okay. So if we look at this CH3, it's attached to a CH2, which is attached to a CH3. Okay. So I'm going to convince myself that this CH3 is identical to that CH3 because of the same connectivity. Do we agree with that? Okay. So those are the same. Okay. So that means this other carbon here, these are different because they are not the same as the 2 methyl groups there. So these are different. So let's start with these. Okay. Those 6 red hydrogens are equivalent, so they give 1 peak. Okay, that's rule number 1. Equivalent hydrogens give a single peak. Okay. Rule number 2, you look for the number of hydrogens that are within 3 bonds. So we have 1, 2, 3, 1, 2, 3. We have 2 non-equivalent hydrogens within 3 bonds of those equivalent protons. So that means our n is equal to 2, which means these and these protons are going to be in a triplet. Have 3 peaks for a total of 6 hydrogens. Okay? Does everybody believe that? Okay, so we're going to have a triplet and it's going to equal to 6 hydrogens. Okay, let's go the other way. So now we're looking at these. center ones right here. Come on. Right here. So we need to identify how many non-equivalent hydrogens are within 3 bonds. So we have 1, 2, 3, 4, 5, and 6. This one down here doesn't count because it's equivalent. So we have 6 right there. So our N is equal to 6. Plus our unique peak is a total of 7. We're going to see 7 peaks here. So that's a heptet. Okay. And we see, if we pull this up real big, we see 1, 2, 3, 4, 5, 6, 7. And on the other peak, we have 1, 2, 3. Okay. Are we starting to see we're splitting? Why is it 2 and not 3? For the number of equivalent hydrogens nearby on the triplet? Okay. Okay. So if we look at this, it's going to be N is equal to 2 because 1 hydrogen here and 1 hydrogen here. But remember, our number is N plus 1 is equal to the number of peaks we see. We still have to split the unique hydrogens by themselves. Okay. So we have 2 hydrogens that are nearby plus the peak itself. So we're going to get a 3 for the red hydrogens. The blue hydrogens, we have a total of 1, 2, 3, 4, 5, 6 nearby. 6 plus 1 is equal to 7. Does that answer your question? I'm looking in the chat box. Okay, good. So it makes sense. That's good. All right, does everybody else get that? Okay. So you can do this the hard way, or you can recognize some patterns here. Okay. So here's some patterns to look for. Okay. If you have 1 hydrogen, 1 carbon over from 1 hydrogen, what you're going to see is this hydrogen is going to give you a doublet. This is going to give you a doublet because they're each only next to 1 other hydrogen. So you get 1 for the hydrogen itself and 1 for the hydrogen nearby. So each is going to give you a total of 2 peaks. Okay. But now if you have 2 hydrogens on this side and only 1 hydrogen on that side, these 2 hydrogens are the same. They get 1 peak plus 1 peak for the red hydrogen. It's a doublet. However, this red hydrogen now has 2 non-equivalents next to it. It gives a triplet. And if we were to add another hydrogen here, so now we have 2 red hydrogens and 2 green hydrogens. These 2 green hydrogens are equivalent and have 2 hydrogens nearby. So that's 2 plus 1 is equal to triplet. These red hydrogens are equivalent plus 2 nearby, giving a triplet. Okay. So let's add 1 hydrogen to the green side and take 1 hydrogen away from the red side. We have these 3 hydrogens here are equivalent and next to 1 hydrogen, so we get a doublet again. We have this hydrogen, but it's got 1, 2, 3, so 1 plus 3 is equal to 4. We get a quartet. Okay, are we starting to, oh, I'm sorry, it's 150, I'm sorry. All right, look at this chart. We're gonna come back to this chart for splitting when we get back, and then we're gonna hit carbon NMR and mass spec when we come back on Wednesday. So sorry I went long. Where's my, there it is. All right. Stop share.